In this video, we're going to talk about trees. Trees are a nonlinear data structure where the elements are organized into some sort of hierarchy. And we'll also talk about the definitions for the parts of a tree, how to implement trees, and we'll also talk about tree traversals. Trees are made up of two components. The first is the nodes of the tree. So that would be things like piece here, and this is where our actual data is going to be stored. The second piece that makes up a tree are the edges. So you'll see that the nodes are connected by edges. So each node is on a particular level. So this is level 0, level 1, level 2, level 3, and level 4. And the most important node is the root node here at the top. The root node will be the one that's stored in our actual binary tree data structure, and we can use the root node to get to any other node in the tree. The way nodes are organized in the tree, we have parent nodes. So let's say this will be a parent, and the parent will have child nodes. So here's two children of the parent that's highlighted in blue. And then we call these two green nodes siblings because they share a parent. Every node in the tree is going to have at least one parent, with the exception of the root node. The root node will not have a parent because it's where the tree, we can think of it as the tree starting. But the root can have its own children. So here this green node and the blue node are children of the root node. And then we say that a node is an ancestor of another node if it's above it in the tree. So for example, if we take this node right here, its ancestors are this node, this node, this node, and the root. The root is the ancestor of every node in the tree. And we also have a descendant relationship where we say that every node is a descendant of the root, and then this node here would be a descendant of this one, this node is a descendant of this one, and so on. So a few nodes have special names. This is a leaf node, and we call it a leaf node because it has no children. This is also a leaf node because it doesn't have children. An internal node has both a parent and a child, whereas a leaf would only have a parent. And then finally, the root node has no parent, but it does have children. Also, the tree is made up of multiple subtrees. So for example, you can see that this right here could be thought of as a subtree with this node as the root. Also, this could be a subtree with this node as the root. So the tree has paths in it, so I can go from the root to this node using the path marked in red. And the level of a node is the length of that path from the root to the node. So in this case, this blue node right here is on level 1, 2, 3, 4. And we say the height of the tree is the length of the longest path from the root to a leaf. So in this case, you can see that these other paths would be 1, 2. Here's one that's 1, 2, 3, 1, 2, 3. So 4 is the longest path from the root to a leaf. So that would be the height of the tree, 4. Now the trees we've seen so far have all been binary trees. We call them binary trees because so far they've just had two children. However, there's no reason that a tree couldn't have more. So here in a binary tree, we have two children, but we can also have a tree that has 3 children, like here, and we can even have a tree that has 4 children. We can call that a quad tree. So we classify trees by how many nodes or how many children they can have at most. So if the most number of children you can have is 2, we call it a binary tree. A general tree would have no limit. In general, if the maximum number of children allowed for a node is n, we call it an n-ary tree. Now here we have what we call a full binary tree. A full binary or full tree of any type is when every non-leaf has the most number of children. So these are all leaves, but this has 2 children, this node has 2 children. So every non-leaf has the same number of children. Also, you can see the root has 2. Then all the leaf nodes are at the same height. So all of the leaves are at height 1, 2. And you can see all the leaves are here. We call that a full tree. Now we can have a complete tree, which would be full up to the next to last level, but then we can add additional nodes as long as we do so from left to right. I can add additional nodes like so as long as I add them from left to right. And then I would add a node here, and so on. Now I want to be careful because if I added a node here, but the tree wouldn't be complete. Complete trees are useful because they're what are called balanced, meaning in every child subtree, the height is within a few levels. So we'll see an example of that next. So the idea of balance is very important in trees. And so let's just draw a tree here. Notice that I'm keeping this tree relatively balanced as I go. And even if the number of leaves isn't the maximum, you can see that this is still relatively balanced because the height of each subtree is approximately the same. And in every case, it's within 2. Now, if we have an unbalanced tree, we could have something like this, where maybe some of the subtrees are relatively balanced, but overall, there's way more nodes in the right subtree here than in the left. And so that would be called an unbalanced tree. The advantage of a balanced tree is that all the leaves are within some fixed amount of the root. And so we can make assumptions about the performance of the tree, like searching through the tree or finding any particular root or node, because any node can only be that height distance away from the root. And a balanced tree minimizes the height. So next we're going to talk about 2 approaches for implementing trees. The first way we can implement tree is by using an array. And here the array is going to hold nodes, and each node is going to have 2 array indices in addition to the element that it holds. So for this array, we could store A here at 0, and that would tell us that that's the root. It's stored in 0. Then its children, the left child is held at index 2n plus 1. So that would be B here, and that's index 1. C would be held at index 2 times n plus 1, which would be index 2. And we would put that in A's node for the right child. So for B, its left child is C. Actually, this should be E. I had the wrong one here. So here, okay, so B has C as its left child. So C would be stored at index, this is index 1. So the left child is 2n plus 1. 2 times 2 is 2, plus 1 is 3. 0, 1, 2, 3. So here we're going to store C. And we're going to make a note that that's held in index 3. B doesn't have a right child, so that would just be null. Now E has D as its subchild. E is at index 2. 2 times 2 plus 1 is 5. And that's where we would hold the left child, which would be here. And its right child would be at 2 times 2 plus 1, so that's index 6. And it looks like I didn't give myself enough room for index 6. So I'll draw an ugly one down here, and that's where F would be. And its child's, it doesn't have any children, D doesn't have any children, C doesn't have any children. So that's what the array-based implementation would look like. One thing to notice is we have this empty spot right here. That's something that we would want to be careful of, because if we don't have a relatively full or a complete tree, then the array implementation is going to waste a lot of space, because for any index I can tell what its parent is. So if you can think about a really unbalanced tree, all of a sudden you're storing the children at 2n away from where the current one is, so you're wasting a lot of space that way. But this works really well for full or complete trees. Now the linked implementation is a little more natural, and it's very similar to what we did with the linked list. So here we would have A, and then its children are B and E. That's a terrible E. And then B has C as a child, and C has no children. B has no right child. E's left child is D, and its right child is F, and neither of those have children. So when we have a tree, we're going to want some way to get everything out of it. Now with a linked list, there's a natural way to pull things out. You just start at the beginning and go through the end. The tree, though, doesn't have a hierarchy, so our traversals are going to be a little more complicated in how they work. So let's see some examples. So in an in-order traversal, we're going to visit the node, meaning we're going to do something. So either add it to an iterator, print it out, do something with the value there. First on the left subtree, then we're going to do the node, then the right subtree. So here, we're going to start at A, but A, since it's an inward traversal, we need to do the left subtree first. So we're going to go to B. Now we have to do the left subtree first, so we have just D. So we'll make a note that we have D. Then we go back to B, then we need to visit the right subtree of B. So that's going to be this subtree where we visit the left first, G, then E. Then we've completed this subtree, so now we're going to visit A, and then we're going to visit A's right subtree. Now this right subtree is pretty straightforward because nothing has a left subtree, so we're going to visit C. There's no left subtree, so we visit C first. Then in its right subtree, F doesn't have a left subtree, so we're going to visit it first. And then H has no children, so we're done. Visiting the right subtree of A, C, F, and H. So a pre-ordered traversal works by visiting the root first. So I'm going to visit A, then I'm going to visit its left subtree, then the right subtree. And I'm going to do that recursively. So with B, I'm going to visit B first, then the left subtree, then the right subtree. So here, I'm going to visit B, then D, then E because it's the right subtree of B, so EG. Then I'm going to visit the right subtree of A, which will be C, F, and H. So with the post-order traversals, they work similar to what we've seen before, except now we're going to visit the root last. So when I want to go with A, first I'm going to visit the left subtree, then the right subtree. When I visit B, I'm going to visit the left subtree, the right subtree, then B. For E, left subtree, first G, then the right subtree doesn't exist, then E. The way this is going to work, if I drew this out, is I would visit A, then B, then I would actually take D, to go back to B, go to the right subtree, which is E. I want to go to its left subtree first, then do G. Then as I backtrack, I take all those roots that I didn't see before. Then with A, I'm going to go to the right subtree. C doesn't have a left subtree, but it does have a right subtree. F doesn't have a left subtree, but it has a right subtree. And then H has no children, so then I do visit the root, and then again I backtrack all the way back up to the root. When I actually write this out, it's going to be D, G, E, B, H, F, C, A. And the final traversal that we want to talk about is level order. Now with level order, we essentially just start at the top and go from left to right. So A, B, C, D, E, F, G, H. So A, B, C, D, E, F, G, H. Now notice those came out in alphabetical order. That has to do with how the nodes are arranged in the tree. It doesn't mean that level order means alphabetical order.